For our second session this morning, we're happy to have Alex here, all the way from Berlin, and he's going to tell us about reevaluating UV divergences in the 1950s.
Yes, thank you very much. So the work I'm presenting here is part of a larger book project on debates on the consistency of quantum field theory after the development of renormalization, so the debates in the 50s and 60s up to the eve of asymptotic freedom, which kind of changed that discussion. Today I'm going to be focusing on a very specific point in that debate. It's a point on which I think there is still a fair amount of confusion to this day, so I hope that this will be not just of historical insight. I know that Mike is also going to be speaking about this issue later today, and the issue that I'm going to be talking about, that I'm going to be focusing on, is the relation between different kinds of UV divergences. So I'm really focusing on this issue, trying to make it as clear as possible using the historical context, but also trying to make that of more general interest. And so I've resisted my historian's impulses and done this very austere black and white slide with no pictures of the historical actors. So see how that worked out. Okay, good. So when I talk about this reevaluation and the various kinds of UV divergences, I'm mainly focusing on two different kinds. And I've had some issues with how exactly to label them. I'm calling them virtual and real here, only to immediately problematize that labeling, but we'll stick with that, and then we can discuss whether people have better names for those. So this reevaluation between the relation between these two is something that indeed occurred in the 1950s, so in the immediate aftermath of the development of renormalization in the late 1940s. So by virtual UV divergences, I mean the usual perturbative UV divergences that one removes by renormalization. So they arise because one is integrating over intermediate states in perturbation theory, and this integration diverges because the contributions from the high energy states don't fall off fast enough. So it's not like any individual high energy state gives like a problematic contribution, but it's the integration over the entire range of possible states that gives you the divergences, and these are of course the ones that one encounters in high orders of perturbation theory, and that were very problematic until they were dealt with renormalization. By real UV divergences, I mean that we have some physical quantity, so not like a term in a perturbation expansion, but the entire expression for some physical quantity, which is a function of energy, and so the easiest example is just a scattering amplitude taken as a function of the center of mass energy, and there I would talk about a real UV divergence when that physical quantity, if we look at it in the limit of large values of its argument, so for large energies, if that actually diverges, so gets an infinite and thus unphysical value, in spite of being actually a function that's supposed to describe a physical quantity. So these are the two kinds of divergences that I want to distinguish here, and the relation between which I want to discuss by following their historical trajectory in the early 1950s, in the wake of renormalization. Okay. And so, please feel free to interrupt me at any point, because it's really just one point I want to make here, and that should be as clear as possible. Okay, so I labeled these two UV divergences virtual and real, because the entities that carry the large energies are virtual or real. So in the one case we're talking about the divergences coming from the contributions from virtual particles at high energies. In the other case we're talking about the actual center of mass energy of some scattering process. But one can also view both of these types as relating to the energies, or rather four momenta squared, of virtual particles. So there we go. So this is a classical example of a perturbative virtual UV divergence. We have the self-energy of an electron that emits and reabsorbs a photon. So we have a virtual particle in the loop. That's where the integration over energies comes from, the energies of this virtual particle here. So, and we get to integrate over arbitrarily large off-shell momenta, and they're unconstrained because it's a particle in a loop. Okay, so those are the virtual UV divergences. And then for the real UV divergences, in a way, that really is also the property of a virtual particle we're talking about there, right? We can, of course, talk about the center of mass energy of this scattering process, so electron-positron scattering in this case. But the center of mass energy is not a relativistically invariant quantity. So if we want to get the energy in question as actually the 4 momentum squared of some particle, that particle is actually the virtual exchange particle here, okay? So this is also a virtual particle. It's off-shell, and it can have, and its off-shell momentum is not arbitrary. We're not integrating over it as here, but it's determined by the scattering energy. So the 4 momentum squared of this photon here will be exactly the center of mass energy, usually noted by S. So it's a virtual particle, it's off-shell, but still we're going to refer to these as real UV divergences because it is still the center of mass energy of a real scattering process. The important thing for us is that when we talk about those quantities that exhibit real UV divergences, okay, so that actually are going to show some sort of pathological behavior for large energies, it is precisely going to be this quantity here, so the modified propagator of the photon. So I drew a tree-level diagram here, but the quantity that also Gelman and Lowe, whom we heard about earlier in James's talk, and whom I'm also going to look at later, the quantity that exhibits these real UV divergences is precisely the photon propagator here. So it's the off-shell UV behavior of the photon propagator, with all radiative corrections included. So the full propagator of the photon being exchanged here in a scattering process between electrons and positrons. Okay, so much for the initial distinction between real and virtual UV divergences. This real, this virtual, and we're going to be saying some more about their relation later on. Okay, we're going to start now with the story of the virtual UV divergences. And these famously haunted quantum electrodynamics from the very start. So here is arguably the first instance of such a UV divergence calculated by Robert Oppenheimer as a postdoc in Zurich. You don't have to see any of the details of what he was, the equation, but what he was calculating here was the displacement of spectral lines in hydrogen resulting from higher order radiative perturbative corrections in QED, and you can see the central feature. We're integrating here over the frequency. There's the integration of an intermediate photon, and you're going to get a logarithmic divergence. Okay. So, so these UV divergences were known almost from the start in the development of QED. They were seen as a huge problem, as inhibiting the actual use of QED as a predictive theory, for example, for calculating line widths or the behavior of cosmic rays. So it was a huge issue all through the 30s and 40s until the development of renormalization. And in this period, there were two main interpretations around for what we should think of these, what we should think about these perturbative virtual UV divergences. So one story was that these UV divergences point to a breakdown of the theory at short distances, right, or high energies. And this view was underwritten by the analogous difficulties that you have in classical theories of the electron, as developed by Lorentz in the late 19th century, where you similarly encounter divergences when you try to put point-like charged particles into the theory. You get similar divergences of the field strengths and the energy within the field close to the particle, and one interpretation was to say, oh, the perturbative UV divergences, they are just the continuation of this classical problem of point-like charges in the quantum theory. And so just like in the classical theory, there was the idea that one would have to assume some sort of assign some sort of finite length scale to the electron to make sense of things, the so-called classical electron radius. The idea was that one would similarly have to introduce some sort of physical cutoff, modify the short distance physics in order to get rid of these perturbative UV divergences in QED. And there were several proposals for that, such as, for example, Heisenberg's ideas about fundamental lengths, which were always related to this classical notion of the classical electron radius. And I'll say a bit more about that in a moment. The other interpretation was that this is an intrinsically quantum problem. This is not an inheritance from the classical theory. This is intrinsic to quantum theory, and it shows that quantum theory in general has difficulties with dealing with infinitely many degrees of freedom. Okay, so that it's not that let's see, if we look here, it's not that the integrand here somehow becomes unphysical for large frequencies, and we need to modify it. And so the problem is not here in the integrand. The problem is really in the integration, in the fact that we're integrating over infinitely many degrees of freedom as intermediate states. And we somehow need to fix something mathematically with quantum theory to make it able to deal with infinitely many degrees of freedom. And the analogy here was not so much classical electrodynamics, but really the similar problems that you would have in the infrared, where you similarly have to deal with the emission of large numbers of very low frequency photons. There were methods for dealing with this developed in the 1930s by Bloch and Nozick in particular, and so that some sort of mathematical fix was needed that would not modify in any way short distance or high energy physics, but rather you would somehow have to, like in IR, in the infrared, somehow find new methods for dealing with infinitely many degrees of freedom in perturbation. So these were the two readings, and arguably, when renormalization was developed in the late 40s, one might say that looking at it in hindsight, the development of renormalization really very strongly would have seemed to underwrite the second kind of view, because it was just a mathematical procedure, right? There was really there was regularization involved there, but the exact parameters that you used to regularize, and so for a short time maybe modify your short distance physics, they did not appear in the actual results of the renormalized theory. There was no obvious cutoff scale that you could numerically, you might use a cutoff scale in your regularization, but there was no numerical cutoff involved. There was nothing pointing, for example, to something like the classical electron radius. There was just, in short, there was no modification of the short distance physics going on in renormalization. And soon, and we'll hear more about this in Mike's talk, there was even like a purely mathematical argument for why these UV divergences arose from the multiplication of divergences. This started in the mid-50s already. So really, renormalization seemed like this kind of formal mathematical method, or could have seemed as this formal mathematical method for QFT, or quantum theory in general, to deal with infinitely many degrees of freedom, and so would have seemed to underwrite that second reading of what was going on. But one has to say that already back then, where's the point of this?
On the computer.
Where is it?
It's flat. Should be back here. I can hit it if you want me to.
Yeah, slide please. Okay, good, thank you. Yet already at the time, the need for renormalization and the perturbative virtual UV divergences were, even after the development of renormalization, widely viewed as relating to problems of the theory for short distances or high energies. And you have a lot of talk in papers by the pioneers of renormalization, by Schwinger and Dyson, that really sound very much like modern day effective field theory talk about, the theory clearly just being being applicable to some certain finite energy scale. There are several reasons for this persistence of interpreting renormalization and the virtual UV divergences as resulting from somehow bad UV behavior. One of those is certainly the appearance of a cutoff in regularization schemes. So even though the numerical value did not matter, there was still a cutoff involved that on a formal level looked very much like the kind of cutoffs that you would have gotten from fundamental length theories, or in invoking something like the classical electron radius. Thank you. Like for example in the regularization schemes of Pauli and Villars. There was also, of course, a clear narrative for why one would anyway need a modification of short distance physics, because everyone knew, except for maybe a handful of people who had some crazy ideas there, like John Wheeler, that one would need new short distance physics to describe nuclear physics. Right? It was clear that QED would not be able to describe beta decay or the cohesion of protons and neutrons in the nucleus. So there was a strong physical reason for believing that short distance physics would require some sort of, well, at least amendment of QED. And this kind of merged with this reading of the UV divergences as coming from faulty short distance physics. This reading was strengthened by a surprising numerical equivalence, which really is a pure coincidence problem, or we view it as one today, namely that the classical electron radius and the scale at which nuclear physics effects become important, so the size of the proton, are approximately of the same order. So this is the classical electron radius, so the electron mass divided by the fine structure constant. This is what we now call the QCD scale, so about the size of the proton. And they're of the same order of magnitude. They're both about 100 MeV, and this was very, very convincing for people at the time. In addition, to top it all off, the muon mass is also of that order, and the confluence of these two really convinced people that here, at about 10 to the minus 13 centimeters, something new had to come in. And so that drove the kind of QED needs to be modified at small scales narrative. And in addition, there was, of course, also a distrust of infinite renormalization as a legitimate mathematical procedure. Many people, like Dirac famously, entirely rejected it. And so there was a feeling that this might just be a stopgap, and really you would have to have some sort of physical interpretation of what was going on in renormalization, and that would involve indeed some sort of modification at short distances. So what we can see here, using the categories I introduced in the beginning, is some sort of conflation, right, of real and virtual UV divergences. And it was really strongly assumed that virtual UV divergences were indeed about the short distance behavior of the field. Okay. So this is to say that quantum electrodynamics was considered untrustworthy above nuclear energy scales. Okay. One didn't think that the theory would be able to say anything about those. But what did the theory actually have to say, right? Because you could, of course, do in principle calculations in QED and see what the theory all by itself had to say about high energy scales. So what about the real UV divergences in QED? Okay. So this had been explored to some extent in the 1940s. And the UV behavior of QED at first order in perturbation theory is perfectly fine. Indeed, in 1940, Wolfgang Pauli made a classification of quantum field theories. On the one hand, there were those that have an ultraviolet finite scattering amplitude in first order perturbation theory, such as QED. And those are the second kind that have UV divergent scattering amplitudes already in first order in perturbation theory. And an example of that is, for example, is Fermi's theory of the beta decay, where the effective coupling constant, which is the momentum divided by what we would now call the mass of the W boson, and basically rises above all limits for high energies. So there was a distinction. QED was on the good side of the UV behavior here, And this distinction later on, mapped perfectly to a distinction between renormalizable and non-renormalizable. But the UV behavior of QED, what it actually predicted, was of course at the time not explored beyond first order perturbation theory, for the very reason that one was not able to do that in before renormalization, right? At second order perturbation theory, you would just get infinite results, UV limit or not, right? So, good. So after renormalization, that changed, right? You could look at what the QED had to say about the UV regime in higher orders of perturbation theory. And here, and this is an equation from the Gell-Mann and Low paper, who are the first ones to really emphasize these points. Here you would encounter so-called large logarithms, okay, if you wanted to look at higher. So the higher order, if you look here, if you look here at the first order term, that's obviously so fine. So this is just the modified electron propagator here as an example. At higher orders, you would get these logarithms of p squared, so the momentum of the particle in the propagator divided by its mass. And these arise from the on-shell renormalization of logarithmic divergences, right? So we have logarithmic divergences when calculating the modifications to, say, the electron propagator. Those are renormalized on-shell, because as James pointed out, right, that was the only mass shell renormalization was the only method available at the time. And then instead of logarithmic dependence on the cutoff, you get these logarithms of p squared over m squared. And so what they show you is, right, that if you want to look at the UV behavior of QED in perturbation theory, then you're going to see these logarithms are going to get very large, right? And so one can clearly see it was obvious that in perturbation theory, the first orders did not give a reliable estimate for large off-shell momenta, because as soon as the logarithm of p squared over m squared is about on the order of 1 over e squared, right? Then if you take this times this as the expansion coefficient, or this times this here, then the perturbation series just does not converge very quickly anymore. So perturbation theory becomes unreliable in the UV. And this was, I think a lot of people had ideas about this, and they didn't think QED was reliable anyway, and it was also an experimentally accessible QED at these energies, so it wasn't a very pressing problem, but it was Gell-Mann and Low who first spelled out this problem of the large logarithms. Okay, so the status was QED at high energies was doubly untrustworthy, both as a theory in general, right, it was supposed to break down, and also the approximation you used, perturbation theory, was going to fail for large energies, so it really seemed kind of inaccessible, but also not very interesting from a phenomenological point of view. But it was then, as James already hinted at, this problem of the UV behavior of QED was then investigated in detail by Gell-Mann and Low. So the paper in which they first developed their renormalization group methods is actually called Quantum Electrodynamics at Short Distances, right? That's the name of the paper. That was the main focus. And here's how they motivated it in the paper. It may be objected to an investigation of this sort that while 1.2, that is an expression for the modified photon propagator, I think, is valid for distances very small, is very small compared to the electron's Compton wavelength. The first few terms should suffice for calculation unless the length scale is as small as e to the minus 137 times the electron's Compton wavelength. That's precisely this limit, right? Just in position space, not in momentum space. And it's a ridiculously small distance, right? So there's really no reason that the large logarithms they become problematic not at nuclear scales, right, but like at much larger scales, like this is like Planck length, we're talking like Planck length kind of stuff. So we have no reason, in fact, to believe that at such distances QED has any validity whatever. particularly since interactions of the electromagnetic field with particles other than the electron, like for example protons, are ignored. However, a study of the mathematical character of the theory at small distances may prove useful in constructing future theories. Okay? And so that is really Gell-Mann and Lowe's prime motivation for looking at the short distance theory of QED, and it's about evaluating quantum field theory as a framework, right? It's about seeing whether one can whether one can construct a quantum field theory that is in principle valid to arbitrarily high energies. And this was, of course, related to questions whether quantum field theory would, for example, be the right framework to describe the nuclear interactions. And so, indeed, this is about evaluating QFT as a framework. That's how it fits into my story about looking at the consistency of QFT. And indeed, outside of the immediate context of the axiomatic framework, where consistency was still understood in terms of looking at the consistency of their axioms or meta laws, in general, outside of that community, UV finiteness became like the main criterion to evaluate the cogency of QFT as a mathematical framework and its possible applicability beyond QED. Okay. So, but what could go wrong, right? I mean, clearly perturbation theory kind of failed, but you might try to develop new mathematical techniques for that. And we've seen right before I gave you this list of points why people continue to believe that the UV behavior of QED was problematic, even after renormalization, and most of those were, kind of spurious. But there is this one point about the distrust of infinite renormalization, right? There was still the fact, right, that you were when you were renormalizing QED dealing with these infinite quantities. So there were divergences somewhere involved in the theory, and they were ultimately the most important reason to believe that something within the theory of QED itself, right, might ultimately lead to the theory's breakdown. So not like coming in of new effects of nuclear physics, but this was really about looking at whether QED itself was intrinsically consistent at high energies. And there was the question of infinite renormalization, which is of course also directly connected to the virtual UV divergences, because that's where infinite renormalization comes from handling the virtual UV divergences of particles in loops. So what I'm going to be talking about in the next 2 or 3 slides is the relation between infinite renormalization and Gell-Mann and Lowe's investigation of QED at short distances, and thus also at the relation between the real UV divergences that Gell-Mann and Lowe were studying, and the real UV behavior of QED, and the virtual UV divergences of perturbation theory and infinite renormalization. Okay. So, and here Gell-Mann and Lowe managed to establish a connection between infinite renormalization and virtual UV divergences on the one hand, and the real UV divergences on the other hand. So for studying the real UV divergences, Gell-Mann and Lowe were looking at, as I was saying before, they were looking at the photon propagator. So you remember the Feynman diagram I had in the beginning, right? If you want to look at the behavior of some scattering process for large center of mass energies, what you're really looking at for electron-electron or electron-positron scattering, what you're really looking at is the behavior of the photon propagator for large off-shell momenta. And so that's what Gell-Mann and Lowe were studying. So this quantity here, this is the photon propagator, the renormalized photon propagator, with radiative corrections, of course, included. And that was the quantity whose UV behavior they were studying. And for that study, they made use of what is now normally called the Schell-Lehmann spectral representation that was simultaneously also discovered by Gell-Mann and Lowe and also by Kamefuji and Mizawa in Japan. The idea, right, that so you have this leading order term, the free propagator, and then you have an integral over propagators of massive particles with mass m, and you're integrating over all of those mass squareds, and then you have a spectral function that weights these propagators, and that spectral function basically comes from inserting a complete set of energy eigenstates in the theory, which you don't have explicitly, of course, but which you insert formally. So there's no direct way to calculate the spectral function. It's just the general form for the problem. And just an example of what one can do with that, or what Gelman and Lowe did with that, is that you can construct a similar spectral representation, right, for the wave function renormalization constant of the photon, which is, because of the Ward identity, exactly equal to the charge renormalization constant in QED. So so this here, right, this here you get basically from inserting a complete set of states into the time-ordered product, the time-ordered VEV, but you can do a similar thing for the commutator of the renormalized fields. And the commutator of the renormalized fields explicitly contains the corresponding field renormalization constant. So these are the renormalized equal time commutation relations, and because of the renormalized fields, we have the Z3 in there. One can do the same thing. Gelman and Lowe did the same thing, and then you get a spectral representation for the charge renormalization constant. Now, which appears as a field renormalization constant for the photon in the Lagrangian. So this is a non-perturbative handle, right, that Gelman and Lowe developed, in parallel also by Chalin, to say something about the renormalization constants outside of perturbation theory. And then you get this spectral expression here, right, which contains the same spectral function, right, because it's the same matrix elements of electromagnetic field operators between the vacuum and some complete set of states. And then Gelman and Lowe pointed out that there was a direct connection here between these two. So if you multiplied the photon propagator with p squared and then took the limit they were interested in, okay? If you took the large off-scale momenta UV limit, you got exactly the charge renormalization constant, right? So by studying, as they were doing, right, the short distance high energy behavior of QED of the photon propagator here, they were also doing a non-perturbative investigation of the magnitude of the renormalization constants, and thereby connecting the renormalization constants that came from the virtual UV divergences with the real UV divergences being studied by looking at the UV behavior of the renormalized quantities. And this is, of course, a generic relation, right, between a two-point function for some field like this here and the corresponding field renormalization. It just is of more importance in QED because the field renormalization constant of the electromagnetic field in this case is precisely the charge renormalization constant, right? There's always issues with the physical interpretation of or was at the time at least, issues with the physical interpretation of the wave function renormalization constant, but the charge renormalization constant had a very clear physical interpretation, and that was the one that Gelman and Lowe offered, right? This was really the starting point of their entire analysis, and the physical interpretation they offered that if we look at the scattering amplitude for high energy very high energy scatterings, the two electrons are going to approach each other so closely that they can actually penetrate the entire cloud of virtual photons and electron-positron pairs and really see the bare charge of each other, and that's why the scattering amplitude for very high energies depends on the bare charge, and you have, that was Gelman and Lowe's discovery, this confluence of evaluating the magnitude of the renormalization constants on the one hand and the real UV behavior of the field. Okay. And that is then the starting point for them to do their renormalization analysis, right? Because as soon as you realize that the limit of the propagator in the UV is the renormalization constant of bare charge, one can then take the propagator itself to be this momentum-dependent, to be a momentum-dependent renormalization constant, and just renormalize at various scales, and that is then what the kind of moving the scale renormalization group that James was talking about. And you then immediately had, since you had this interpretation of the bare charge now as the charge that two electrons scattering off each other see when they scatter very high energies, you had an immediate physical interpretation of these other charges as the charge, the effective charge seen by the electron at lower scale energies, and thus, to some extent, the idea of the running charge. They were able to obtain the RG equation for this charge, and this is what it looks like in Galman-Lo. You can still see the connection between this is the running charge, but it's also connected with with some normalization of the photon propagator. So those two things are not very much entangled there yet. In modern presentations, you would just talk about running the charge itself. And to address the question of how perturbative this was, right, they did manage to express these relations independently of perturbation theory to some extent. Right, there's no direct reference to perturbation theory. You can calculate the beta function in perturbation theory, but this expression is in a way non-perturbative. The way they derived it was to say, oh, we're going to look at features of the entire perturbation series, and then we're going to assume that if each summand in the perturbation expansion has a certain property, that the actual function should also have that property, independently of whether the perturbation series converges or not. And from that you can derive then these functional equations like this. That was their method. It was in a way going beyond perturbation theory, but very much perturbation theory inspired, because the properties that went into their functional equations were determined as properties that every term in the perturbation expansion has. And as James already mentioned, right, okay, so that's that. You have this equation. You could calculate the beta function in perturbation theory, but then you'll just get the perturbation result back. But you know that there might be non-perturbative effects here. And so the renormalization group equation doesn't really tell you anything about UV finiteness, but at least it doesn't rule out the fact that QED might be UV finite. So the central question for them became, after Gelman and Lo, was, is QED finite in the ultraviolet, or equivalently, is renormalization, or more specifically charge renormalization, finite? Right? These became equivalent questions, and they were really the dominating questions concerning the consistency of quantum electrodynamics in the decades after that. Of course, things were then totally changed with in QCD, right, where you have a manifestly well-behaved charge renormalization in the UV. The answer of perturbation theory was now also obvious. So back to the 50s and just to QED. The answer of perturbation theory was also obvious now, right? Perturbation theory predicts that QED diverges in the UV, but the question remained whether this was also true in some non-perturbative set. And this is the main part of the debate that I'm chronicling, because there were really very opposed views there. So Gunnar Schelen, he had a proof in 1953 that indeed renormalization continued to be infinite non-perturbatively. Gelman and Lo argued against it, that not necessarily, right? The renormalization group equation can take us in different directions. And then, of course, in the mid-50s, Landau and Pomeranchuk is actually even worse than in perturbation theory, because we get a Landau pole, we actually get an infinite charge and infinities in the photon propagator already at finite energies. We don't even have to go all the way to infinite energies. So this was a debate that really went on and was not resolved, but only transformed, let's say, by the discovery of asymptotic freedom. Right, okay, that's what I just said, yes. So after asymptotic freedom, right, a narrative emerged also by the discoverers of asymptotic freedom. So David Gross made a big point of this, that now they had managed to banish the Landau ghost, right? There were things that manifested did not have a Landau pole, but actually, if you look at the sources, while the Landau pole was very popular and believed in the East, it was actually largely ignored in the West all the way in the 1970s. Okay, and And what asymptotic freedom also showed then was that the question of UV finiteness was not like some generic feature of QFT, right? You couldn't figure this out for QED and then know whether quantum field theory was a good framework or not, but you had to check this model by model, and QED was not at all the gold standard of quantum field theory that it had been made out to be. So the validity of QFT no longer stood and fell with the UV behavior of QED. Okay, so to summarize what I talked about, the distinction between virtual and real UV divergences, the way in which virtual divergences continue to be identified as ultraviolet even after the development of renormalization, how Gelman and Lowe discovered this non-perturbative relation between the two, between the magnitude of renormalization and the real UV behavior of scattering processes in QED, and how, and that's maybe what I'll be talking about next time when we have an occasion like this, how then UV finiteness really became the central issue in the assessment of QFT going forward. I briefly hinted at that in the end, but that's this was one chapter that many more chapters follow later on about these debates about UV finiteness. Okay, I'll leave it at that. Thank you very much for your attention, and we're looking forward to your questions.
All right, I see Chris.
I was just curious how Dyson's argument about the failure of convergence of the perturbative series figures into the story. So if I remember correctly, it was from 1949. And so I'm curious whether people responded to that as part of this discussion.
Good, yes. So, yes, that's of course another, a third kind of divergence that comes in here. That's the overall divergence of the perturbation series. Dyson comes up with that in 51. It's part of his program to, so it's a similar program to what Gelman and Lowe are doing, right? Namely to say, we want to show that QED is a, at least potentially self-consistent theory and complete, even though we know it's phenomenologically not complete. We can see QED as a blueprint for quantum field theories of the nuclear interactions. And that was Dyson's program up until 1951, when he finds the non-convergence there. And his program was really to show, if we sum the perturbation series and it converges, we've actually found solutions to the dynamical equations of QED, and that's how we're going to prove that it's a consistent theory. This, so there's not so much like positive reactions to the divergence. People don't really try to resolve the issue all that much. But what is clear is that this path of explicitly constructing solutions to QED is kind of off the table, right? People will then gradually start building up doing that with toy models, and that develops then also in constructed QFT. But the explicit construction of solutions to dynamical equations is really kind of shelved after that. And so that's why I would argue that there's a shift kind of in the way people talk about consistency, right? It's no longer about constructing exact solutions. That seems out of the question. Instead, it's now related to this kind of study of parallel study of UV behavior and the non-perturbative reality of the infinities in renormalization.
David.
This is it's quite an answer to question. So when I think about Gelman-Lowe techniques that get used in modern QFT, I mainly think of them as a practical technique that says I've got I know the parameters at this scale, but I want to study at this scale, and it's inconvenient and calculationally inaccurate to try to do a perturbation theory at one energy scale using perhaps another energy scale. So I want to flow to a new energy scale and do it. And that seems to be the practical modern thing I wanted for. And as you say, in QED that's a luxury at best because the contributions are quite small, but it gets important later. So do you know when that kind of more practical exploitation of the Gelman-Lowe technology started being important?
Yes. I'm not entirely so. I mean, this is this happens as I've not studied this in detail, but I think these developments are a few years before the development of asymptotic freedom. So in the late '60s, I think, with then also with like the development of the Callan-Semantic equation, things like that. That's I think late '60s and early '70s, and indeed it only becomes relevant when you have one way to think about it is right there you have, say, in strong interaction physics, you have a coupling constant that has a magnitude that you don't like, and you want to move it to a value that you do like, and you can do calculations with. In QE, it's the exact opposite. You have a value for the coupling constant that you like, and you want to make sure that it doesn't go bad anywhere, right? And that's what Gell-Mann and Low are doing. So we can really see, it really is just an inversion in a way of that. But that really only happens when, yes, the problem of large coupling constant QFT gets tackled in earnest. And Wilson, so I mean, is a pioneer because a lot of people in the 50s around this time, right, are really thinking, well, the large coupling constant just makes QFT essentially inapplicable to the strong interactions, right? And that's about the rise of S-matrix techniques and all that. And so that's a context, right, in which the Gell-Mann-Low argument can also be understood, right? Precisely to say, well, it's an argument that even where perturbation theory fails, we might still be able to use QFT.
Because that wasn't quite what I meant. I more had in mind that I've got coefficient. It's a value I kind of like. I can do some perturbation theory here, but it's not accurate because the thing I want to calculate is this energy scale that's 2 orders of magnitude separate, and the large logarithm terms with the large neglect in QED are problematic because my scales are larger.
Yes.
So I'll do a better perturbation theory if I have a normalization to improve it and flow up to this scale. So not, I mean, totally agree, of course. In the asymptotic free cases, I'm using the framework qualitatively to say the theory might be manageable at high energies, even though it's more low energies. I'm interested in the quantitative use of it to just make calculations incrementally more accurate.
Okay, so between two perturbative regimes, essentially, but just getting faster converging. My assumption is, but I don't know that this only happens in the 70s in the framework of QCD. But maybe James knows more about this.
Yeah, I think so. This concept of realization group improvement, it definitely becomes a bit more common in QCD. But there is this guy. Because I was looking at this period where no one talks about the realization group. So I was just searching all of the references to it on the show. There's one guy, Erickson, who is working on like precision tests of QED, and he is basically kind of like developing those kind of ideas about using the realization group to improve but yeah, that's kind of a very like minority concern in that period, but it becomes a really big issue.
Carl.
On the same vein about the relation between the normalization group on some by itself and all the story telling, which is all centered on the divergences, one way or the other. So let's make this point. If you look at all this discussion from the perspective of the future, in the current quantum gravity theories, which are being studied, the best studied one, like string theory, quantum gravity, both theories just have not been to divergences, period. This doesn't take anything away from the utility of the normalization group as a tool that connects the prediction theory to the scales. It tells us something about how the theory, how the prediction and the theories of different scales are related to one another. So, in a sense, even if you take away all the great confusion of the 30s, 40s, 50s, and 60s, and maybe later about what actually happens, the revelation group remains as a tool with all its power and its interest, independently of all that. It really is. This is somehow the same direction which is.
Sure. I mean, it's obviously that. I mean, the renormalization group here, right, is also. I mean, in Gelman and Lowe, is not intrinsically connected to the problem that they're studying. It's a tool, right? The problem. I mean, that's why I was saying they don't call the paper renormalization group methods. They call it QED at small distances. That is the issue they're interested in, and they use the renormalization group as a tool to study that. They don't get very far with it, obviously, right? Because they all they ultimately do is write down the equation, say, well, you know, this equation could go this way or that way, right? Depending on what the beta function is. Though they don't actually realize the possibility of a Landau pole. So on the one hand, right, the separation between the method and the questions being asked is there already, and actually, right, it's not even a very good method for studying those questions. It's not like Gelman and Lowe are able to make some sort of robust statement there about the UV behavior. They just like say, okay, well, here's in principle a method for letting the coupling constant run, and it's not a priori clear that the perturbative evaluation of that is going to be reliable. In a way, right, there's because you're trying to cross like a huge scale difference there with realization, like from basically from zero, where you you do your mass shell charge renormalization all the way up to infinity, right? You're spanning the entire landscape of energies there, and it's probably not the best tool for that, right? So in a way, it is more, its utility is greater if we're like moving in between two regimes that we know and want to talk about the relations there. So I think indeed it's a technique that they develop here that can maybe open up the possibility that one can talk about this whole thing non-perturbably, but is not like readily applicable there necessarily, and that is that partially explains precisely the longer period, or one explanation for the longer period in which nothing happens with the renormalization group, because it was developed to study a problem where it's not really that's not like its prime strength in a way. Yeah.
So I'm going to insert myself. You brought up the S matrix theory, which I know is a whole different story, but I'm interested in maybe even just at a sociological level. You distinguish between a couple of different senses in which, just go back to the coupling regimes in which you could have inconsistencies, right? And the virtue of the Gelman-Lowe method was it allowed you to at least think perturbatively about the you define it, like the real UV divergences. So that kind of mathematical project is trying to figure out whether even in for weak coupling, QFT is a consistent mathematical framework. How did that, and then you pointed out, look, you couldn't tell anything about the non-perturbative regimes, there's a variety of opinions. So how does that kind of distinction and debate then feed into thinking about alternatives?
Right. There is certainly there's certainly some connection there in that those people who most strongly argue that. So I mean, a prime example is Landau, right? So he develops an approximation method which is basically deals precisely with the problem of the large logarithms by doing this a leading logarithm expansion, and basically assuming that e squared times those large logarithms is small, and then making an expansion in that. And from that he obtains the Landau pole result, right? And he obtains like a specific claim, the most specific claim in the 1950s about the UV behavior of UV. Namely that it's highly pathological, and diverges at quantum energies. And Landau then, after some wavering, like immediately starts postulating the depth of quantum field, right? And starts working on somewhat idiosyncratic but still S-matrix related stuff. So at least in that one case, there's a clear connection between arguing for the UV difficulties of QED as obtained in some sort of approximation and the turn to S-matrix theory. I wouldn't say that this is like universal. There's not like one can say, oh, you know, the development of the discovery of UV difficulties in QED directly leads everybody into the S-matrix, but at least in some cases, there's a direct personal connection that people use this. And even those that don't have that trajectory in the S-matrix will tend to like kind of gratuitously bring in the insecure UV status of even QED as a motivation for why we should do other things in QFT, even if that's not like, you know, a strong part of their argument or part of their personal trajectory. It becomes kind of, you know, part of the staple argument that you find in the introduction of papers.
Just in view of the ambiguities that occur in perturbed calculations due to renormalization, how seriously can you take precision predictions of such things as the anomalous moment of the muon?
Okay. I'm not quite sure what kind of ambiguities you're referring to here, because the idea is precisely that at least no matter what sort of ambiguity, say, in the renormalization scheme you might have, the success of renormalized QED was built precisely on the fact that you get there were like some debates in the late 40s about the matching between the infrared and the UV and stuff like that. But in general, I mean, that is really what the acceptance of renormalization, in spite of all its conceptual difficulties, was built on, that a consensus could be reached about precision predictions. Of course, for the muon, as far as I know, I'm certainly no expert there, you of course have issues coming in because you get electroweak and QCD corrections in the loops, which are, let's say, less under control, especially if in QCD you're looking at the non-perturbative regime. But that is really not, certainly when Gelman and Lowe say are talking about QED at small distances, they are very explicitly, you know, talking about regimes that are far away from any kind of experimental accessibility, right? There is, I think, a very general consensus at the time after, say, Dyson's proof of renormalization to all orders that QED, at least to order 100, if we can ignore nuclear physics effect, is an unambiguous and very, very precise theory. And I think for the story of the anomalous magnetic moment of the muon, right, I'm not aware that people in any way would want to pin this on QED. Right? The precise question is whether some sort of new physics effects that are not related to QED, but to some different phenomenology come in there. So, how would you?
It's just that there's different schemes. You can use momentum subtraction or minimal subtraction. And the answer that you get at any finite order perturbation theory is contingent upon which choice you make.
Right, so these are the kind of truncation ambiguities, right? I think that James was talking about there. This is not an issue or not a strong issue. I think that's debated in QED, precisely also because I don't think this really comes up. So in the kind of because it doesn't come up in these kinds of mass shell renormalization. Right? There was no, as James was already pointing out, there was no talking about the ambiguity in the subtraction. The subtraction was really pretty clearly defined on with regards to features of the 2-point functions at certain energy scales, which you could then vary, but the subtraction at those scales was not debated at the time. And as far as I know, the effects of that should also be pretty small in QED. So.
I don't think it was even understood.
No, I don't think so. Yeah.
It wasn't even really raised as an issue until like the late 70s.
Yeah. I think it was already, already a step here that in the formulation of your renormalization condition, you could vary the scale at which it was applied. That you would also vary the form it took. I mean, there were of course attempts to do to write down non-perturbative renormalization conditions. So this is what Gunnar Schelen is doing in parallel here. But those were never meant for calculatory purposes. Those were used to derive theorems, as for example Schelen's theorem that the persistence of infinite renormalization outside of perturbation.
I was just wondering if you could say a little bit more about one thing that struck me as a theme that's common to both the talks, which is that as we look at quantum field theories, it's not just QED, but also QCD, and they weren't mentioned as much, but presumably also the theory of the weak interaction, the Fermi theory, and then gravity as well. So there's a sense of, the impression one gets is that historically there's a sense of how to understand divergences based on QED, and that what we see is a sort of, as you think of QFTs as much more general, you have to change the story quite dramatically. And I was wondering is that the right picture to have, do you think, or is there more subtlety that you'd add?
I think that's the right picture. If I were to add any kind of subtlety to that picture, I would say, of course, already in the 50s, we have a certain diversity of quantum field theories, right? People are exploring the meson theories of the strong interaction, the Fermi theories, of course, there already. There are first explorations into quantum gravity. But the general assumption is that QED is the ideal quantum field theory. And that's what certain theories are constructed after. So the theories of the nuclear interaction are constructed after QED. The Fermi theory looks quite different, right? We've seen already that in the 1940s, right? There was this classification, which is ultimately the renormalizable, non-renormalizable distinction. And they're not being like QED was just viewed as a blemish. That's something that you would have to change there. And also, all of the quantization of gravity that goes on a lot of that is exactly built on the blueprint of renormalized QED. So I think what really changes those attitudes is not just the existence of other field theories to be used in other domains, but the precise appearance of QCD as a theory that seems to be better than QED in certain regards, right? Better behaved in the UV. That I think is the decisive turning point, and that then also transforms to a certain extent discussions of gravity, right? Because QED is no longer the thing that you need to aspire to in that regard. So that's what I would maybe, to add a nuance, identify as the turning point in that regard.
All right, thank you. Let's, we're now going to go for lunch. Is that again on the fourth floor, Chris?
Yes.
Okay. But let's thank